Nevada looks still from the surface, but deep below its basins and ranges, the crust is under strain. Small earthquakes can move in clusters, revealing hidden pathways through fractured rock. Most fade quietly, but some patterns raise important questions for cities, roads, water systems, and power lines, like subscribe, and follow this calm journey into the moving ground beneath Nevada. Nevada rests within the dry interior of the western United States, far from the shifting coastlines of the Pacific Ocean, yet deeply connected to the motion of the earth beneath that coast. The state occupies a wide region of high desert, pale valleys, and long mountain chains that run mostly from north to south. From space, the land appears folded into repeated bands of shadow and light. The pattern stretches across hundreds of kilometers and continues into neighboring states. The shape of the landscape reflects a slow and ongoing process that affects nearly the entire western interior of North America. The ground beneath Nevada changes continuously, though the movement remains too slow for ordinary human senses. Over many years, careful measurements from satellites and ground instruments reveal that parts of the region drift by small amounts each year. These motions occur because the outer shell of the Earth, called the crust, does not form a single unbroken surface. Instead, it consists of large pieces known as tectonic plates. The western edge of North America lies near the boundary between the Pacific Plate and the North American Plate. Along the coast of California, those plates slide past one another. Farther inland, the strain from that movement spreads outward across a broader region, including Nevada. The desert surface gives few immediate signs of this hidden motion. In many places, the valleys appear still and empty beneath wide skies. Dry lake beds collect pale dust. Sparse shrubs cover gravel plains. Seasonal rivers vanish into the ground before reaching the sea. During summer, heat rises from the stone in trembling layers. During winter, snow settles along the higher ridges. Yet the apparent calm conceals a crust under tension. Nevada belongs mainly to a geologic province known as the Basin and Range. In this region, the crust slowly stretches apart. As the crust extends, large blocks of rock break and tilt. Some sections sink downward to form valleys, while neighboring blocks rise into mountain ranges. The process unfolds over millions of years, but it continues in the present. Earthquakes provide one of the clearest signs that the crust remains active. An earthquake occurs when accumulated stress inside rock suddenly releases along a fracture called a fault. The release sends waves through the ground. Some earthquakes remain too small for people to feel, while others damage roads, buildings, pipelines, and electrical systems. Nevada experiences thousands of earthquakes each year, though most are weak and detectable only with sensitive instruments. The state ranks among the most seismically active parts of the continental United States. The pattern of seismic activity does not remain fixed. Certain areas grow quiet while others awaken. In some regions, earthquakes cluster into swarms that migrate slowly across the landscape over days, months, or years. Scientists study these moving sequences carefully because they may reveal how stress travels through the crust. Observations indicate that some migrating earthquake patterns involve the movement of underground fluids, while others reflect the gradual transfer of stress between connected faults. It remains uncertain whether all migrating swarms share the same causes. The wider setting around Nevada helps shape these events. To the west lies the Sierra Nevada, a long mountain range lifted high above the desert basins. Beyond it, California marks the main boundary between tectonic plates. To the east, the Basin and Range province extends toward Utah. The entire region forms part of a broad zone where the crust experiences extension and sideways motion at the same time. The climate adds another layer to the surface appearance but does not drive the deeper tectonic processes. Dry conditions preserve fault scarps, which are steep breaks in the landscape formed by ancient earthquakes. In wetter climates, rainfall and vegetation can erase these features more quickly. In Nevada, many remain visible for thousands of years. Long, straight ridges, abrupt steps in the ground, and displaced layers of sediment preserve evidence of repeated motion. From aircraft and satellite images, geologists trace faults across valleys and mountainsides. Some faults cut young sediments, indicating recent activity. Others remain older and inactive. The active structures form networks rather than isolated lines. Stress spreads through this network unevenly. One region may stay quiet for decades before producing a burst of earthquakes. Another may release strain gradually through many smaller events. The crust beneath Nevada also varies in thickness and temperature. Some regions contain unusually warm rock at depth. Heat rises closer to the surface than in many other parts of North America. This heat supports geothermal systems, where underground water becomes hot enough to produce steam. The presence of heat and water may influence local seismic behavior in certain areas. Observations from geothermal fields show that changes in underground pressure can sometimes affect small earthquake activity nearby. Despite the frequent earthquakes, catastrophic events remain relatively uncommon. Much of Nevada has low population density, with large distances separating towns and infrastructure. Yet the state also contains growing urban centers connected by highways, power lines, reservoirs, mines, and communication systems. The interaction between expanding human systems and active geology increases concern among scientists and emergency planners. The modern understanding of Nevada's seismic behavior develops slowly through decades of observation. Early settlers notice occasional shaking, but systematic monitoring begins much later with the spread of seismometers. These instruments measure tiny vibrations within the earth. Networks of sensors now record thousands of small events each month, allowing researchers to map seismic patterns in remarkable detail. Some migrating earthquake sequences become visible only after the installation of dense modern networks. Satellite measurements add another layer of information. Radar instruments carried aboard satellites detect subtle changes in ground elevation after earthquakes. Global Positioning System stations measure slow crustal movement over time. Combined with field observations, these tools reveal that Nevada remains in motion even during long quiet periods. The landscape itself reflects the accumulated result of countless ancient earthquakes. Every tilted range and sunken basin records repeated deformation over immense spans of time. The present terrain represents only a temporary stage in an ongoing process. Valleys fill with sediment carried from nearby mountains. Faults lift fresh ridges. Erosion cuts through rock. Dust settles across dry plains. Beneath it all, stress continues to build slowly within the crust. The migrating earthquakes that concern researchers today emerge from this larger setting of gradual extension, distributed strain, and fractured rock. They do not appear as isolated curiosities. Instead, they form part of a living tectonic system that reshapes Nevada continuously, often invisibly, beneath its quiet desert surface. Across Nevada's surface, the Basin and Range province appears as a repeated arrangement of long valleys and narrow mountains. The pattern gives the state its broad visual rhythm. A range rises sharply from a valley floor, runs for many kilometers, then lowers toward another basin. Beyond that basin, another ridge begins. This sequence continues across much of the state, producing a landscape of parallel forms that seem orderly from a distance and more broken at close range. The outer surface of this region is shaped by extension, which means the crust is being pulled apart. As rock stretches, it does not behave like soft material at shallow depths. It breaks along faults. Large blocks of crust drop downward beside blocks that remain higher or rise relative to them. Over long spans of time, the lowered blocks become basins, and the higher blocks become mountain ranges. The motion is slow, but the result is large. Nevada's valleys and ranges are the visible expression of deep strain spread over a wide area. Many valleys are filled with loose sediment, wind, water, gravity, and rare floods carry broken rock from mountains into the basins. Coarse gravel gathers near the range fronts. Finer sand and silt move farther outward. In the lowest places, dry lake beds may form flat pale surfaces where water once collected or still gathers briefly during wet periods. These sediments can hide faults beneath smooth ground. They can also preserve signs of past surface rupture when a fault cuts through young deposits. At the base of many ranges, the land changes abruptly from steep rock to sloping fans of gravel. These fans form where streams leave narrow mountain canyons and spread across open valleys. Their surfaces often hold clues to recent movement. A fault may cut across a fan as a low step, a straight edge, or a broken line of small scarps. A scarp is a steep slope created when one side of a fault moves relative to the other. In Nevada's dry climate, these features can remain visible for thousands of years, softened but not erased. The mountain ranges themselves are not simple walls. They contain tilted beds, fractured ridges, old volcanic rocks, granite bodies, limestone layers, and folded remnants of earlier geologic worlds. Some ranges expose rocks that formed in ancient seas. Others contain volcanic deposits from eruptions that took place long before the present landscape reached its current form. The surface may look dry and still, but each ridge contains a record of older environments, buried pressure, heating, uplift, and erosion. The valleys form the quieter parts of the scene, but they are not passive spaces. They accumulate sediment that can deepen for hundreds or thousands of meters. Beneath the flat floors, buried faults may continue moving. During strong shaking, loose basin sediments can respond differently from solid bedrock. They may amplify certain seismic waves, making shaking last longer or feel stronger in places where people live, build roads, or place pipelines. The effect depends on sediment thickness, water content, wave frequency, and the shape of the basin. From above, Nevada's basin and range pattern shows how deformation is distributed rather than concentrated in one single crack. A fault may bound one side of a mountain range, while another fault lies across the valley or along the next ridge. Some faults are long and clear, others are short, curved, buried, or partly inactive. The crust responds through a network of fractures. This network gives earthquakes many possible places to begin, though only some faults are ready to slip at any given time. The surface also shows that time is uneven in the landscape. A fresh fault scarp may cut young sediment with sharp edges. An older scarp may appear rounded, partly covered by dust and gravel. A mountain front with steep triangular slopes may indicate repeated uplift along a fault. A gentler front may show more erosion or less recent movement. Geologists compare these shapes with field measurements to understand which faults have moved in the recent geologic past. In the basins, water leaves subtle signs. Even in a dry state, streams carry seasonal flow from snowmelt and storms. Groundwater moves through buried sediments. Springs appear where underground flow meets the surface. Minerals may collect in pale crusts across playa floors, which are flat desert basins that sometimes hold shallow water. These surface water patterns do not create Nevada's tectonic setting, but they influence erosion, sedimentation, and the visibility of fault traces. The stretching of the basin and range does not occur evenly everywhere. Some areas show more recent deformation than others. Some ranges rise more sharply. Some basins are wider and deeper. The surface records this variation in slopes, drainage patterns, and fault scarps, where the crust has extended more strongly. The relief between valley floors and mountain crests may be large. Where motion is slower or older, the features may appear more subdued. Earthquakes in this surface region can rupture the ground directly. When that happens, a fault may create a new break across roads, fences, stream channels, or desert surfaces. One side may rise or drop by centimeters, meters, or more during a large event. Most earthquakes, however, do not break the surface. They occur at depth and send waves upward through rock and sediment. The surface response depends on the path those waves take and the materials they cross. The open land can make Nevada's earthquake hazard appear distant, but the surface tells a steadier story. Roads often follow valleys because they offer easier passage between ranges. Towns grow where water, mining, transportation, or trade make settlement possible. Power lines, rail routes, and communication corridors also use the basins. These same basins can contain young faults, soft sediments, and hidden structures beneath flat ground. The landscape that makes movement across the state possible also carries traces of the forces that continue to reshape it. Within the basin and range surface, stillness is a matter of scale. A valley floor may remain unchanged through a lifetime. A mountain front may seem permanent, yet over many lifetimes, faults shift, ranges rise, basins deepen, and sediments thicken. The surface becomes a calm record of slow extension, written in ridges, scarps, gravel fans, dry lakes, and long shadows across the desert floor. Along Nevada's western side, the surface pattern changes from simple stretching into a wider zone of sideways motion. This region is known as the Walker Lane. It forms a broad belt of faults and broken crust that lies between the Sierra Nevada to the west and the basin and range interior to the east. It does not appear as one single line on the ground. Instead, it spreads across many valleys, ranges, basins, and fault strands, each carrying part of the motion. The Walker Lane helps accommodate the movement between the Pacific Plate and the North American Plate. Along the main coastal boundary in California, much of that motion occurs on the San Andreas Fault System. Farther inland, some of the movement is transferred into eastern California and western Nevada. In this inland region, the crust bends, breaks, and slides in a distributed way. The motion is slow, but it is measurable with modern instruments. The surface expression of the Walker Lane is more complex than a straight valley or a single mountain front. Faults trend in different directions. Some faults move mostly sideways, with one block sliding past another. This motion is called strike slip, meaning the main movement follows the length of the fault. Other faults move mainly up and down, with one side dropping relative to the other. Many faults combine these motions. The result is a mixed pattern where extension and shearing occur together. In northwestern Nevada, this broad zone includes valleys, volcanic fields, dry basins, and mountain blocks that do not align as simply as the ranges farther east. Some landforms bend or step aside. Some basins appear pulled open between faults. Some ridges show signs of rotation. These shapes reflect the way crust responds when sideways motion is spread across a wide area rather than concentrated along one narrow break. The Walker lane does not move at the speed of a visible flow. It changes by millimeters each year, a scale that requires repeated measurement over long periods. Global Positioning System stations record small changes in position. Satellite radar can detect ground deformation after larger earthquakes. Geologists also study displaced stream channels, offset ridges, and broken surfaces to understand movement over longer time. Together, these observations show that the region remains active. The faults of the Walker lane are not all equally active. Some carry more motion than others. Some have ruptured in large historic earthquakes. Others show evidence of older movement but little recent activity. Faults may also be segmented, with separate sections divided by bends, steps, or changes in rock type. A rupture may stop at one segment boundary, or under some conditions continue across it. Observations indicate that fault geometry strongly influences how earthquake sequences unfold. Earthquake activity in this region often appears in clusters. Small events may gather along a fault strand, then shift to nearby structures. In some cases, earthquake sequences seem to migrate through the crust. Their locations change gradually over time, producing a pattern that may trace stress transfer, fluid movement, or both. The exact cause can vary from one sequence to another. Scientists do not treat all migration as one single process, because the observations differ between regions and depths. The western Nevada surface helps preserve evidence of these active structures. Dry climate and sparse vegetation allow subtle breaks to remain visible. A fault may cut a fan of gravel near a mountain front. Another may offset a stream channel by a small distance. A low ridge may rise where compression occurs along a bend in a strike-slip fault. A small basin may open where faults step apart. These landforms are modest compared with the largest mountains, but they carry important information about active deformation. In the Walker lane, the relation between surface faults and deeper earthquake sources can be difficult to trace. A surface line may represent only part of a deeper system. Some earthquakes occur below buried structures that leave little visible mark. Other faults appear clear at the surface but produce few recorded earthquakes during the short period of modern monitoring. The absence of recent small earthquakes does not prove that a fault is inactive. It may simply be locked, quiet, or poorly observed. The region's geology also includes volcanic rocks and geothermal areas. Heat, fractured rock, and groundwater interact in some basins. These conditions can influence small earthquakes locally, especially where pressure changes occur in the subsurface. However, the broad tectonic motion of the Walker lane comes from plate boundary forces and crustal deformation, not from shallow heat alone. The surface contains both long-term tectonic structures and local systems shaped by water, heat, and rock permeability. Cities and towns along the western edge of Nevada sit near this active belt. Reno, Sparks, Carson City, and smaller communities occupy valleys close to known faults. Highways, rail lines, water systems, and power corridors cross the same region. The broad nature of the Walker lane means that seismic hazard is not confined to one obvious fault line. Instead, the hazard is spread across a zone where many structures may contribute to shaking. The historical record in western Nevada includes significant earthquakes that show the ability of the region to release strain suddenly. Some events have produced surface rupture. Others have caused strong shaking without leaving a simple, continuous break at the surface. These differences reflect the complex structure of the fault network. A single earthquake may involve several connected strands or occur on a hidden fault beneath basin sediment. The Walker Lane's motion also influences how scientists view Nevada's long-term tectonic future, though the present evidence remains focused on measured deformation and observed earthquakes. The region is an active part of the boundary between large moving plates, but its behavior is distributed and uneven. Some zones concentrate strain, others move more slowly. The pattern changes from north to south and from west to east. At the scale of the surface, the Walker Lane is a landscape of quiet displacement. Valleys open between fault blocks, ridges shift by small amounts, sediments collect over buried structures, fault scarps soften under wind and rain, instruments record motion that the eye cannot follow. Earthquakes mark moments when accumulated strain releases. In this western belt, Nevada's migrating earthquakes belong to a wider system of shared motion, where the crust does not break along one boundary, but across many connected paths. Nevada's active ground becomes more consequential where people, buildings, roads, and lifelines gather along the edges of valleys. The state contains large empty spaces, but its population is not evenly spread. Communities cluster where water, transport routes, mining districts, state government, tourism, and trade have shaped settlement. These places often occupy basin floors and range fronts, the same surface regions where young faults, soft sediments, and buried structures may be present. Reno and Sparks sit in northwestern Nevada near the eastern side of the Sierra Nevada and within the wider Walker Lane region. The urban area spreads across the Truckee Meadows, where the Truckee River crosses a basin bordered by mountains. The valley floor provides flat land for homes, airports, roads, rail lines, warehouses, and public buildings. Beneath parts of the basin, sediment has accumulated over time. During shaking, these sediments may influence how seismic waves move through the ground. The effect varies from place to place, but the general concern is well established in earthquake science. Soft or thick sediment can sometimes increase shaking compared with nearby bedrock. The built environment around Reno and Sparks reaches toward nearby range fronts. Some slopes are steep, and some alluvial fans carry roads and neighborhoods outward from the basin center. An alluvial fan is a sloping spread of gravel and sand washed from a mountain canyon. These surfaces are useful for building because they stand above the lowest valley floor, but they may also cross older fault traces or lie near active structures. The relation between a building site and a mapped fault can be direct in some places and uncertain in others, especially where sediment covers the ground. South of Reno, Carson City lies along the eastern foot of the Carson Range. The city occupies a narrow valley corridor that connects government buildings, residential areas, highways, and water systems. Mountain fronts rise close to the urban edge. The topography is clear and immediate, with steep slopes to the west and open basin surfaces to the east. Such settings are common in the basin and range, where the practical advantages of valley settlement meet the geologic reality of nearby fault-bounded ranges. The Carson City area carries particular importance because it contains government functions and regional infrastructure. Earthquake risk is not only a matter of how many people live in one place, it also concerns the services that must continue after strong shaking. Emergency response, hospitals, transportation, water delivery, power distribution, and communication systems depend on networks that cross the same ground. A moderate earthquake near a critical corridor can affect areas beyond the damage zone by interrupting movement, supply, or service. Farther south, the Las Vegas Valley forms Nevada's largest urban region. It lies in a broad desert basin surrounded by mountains, The city and its surrounding communities contain millions of residents and visitors, along with airports, highways, hotels, hospitals, schools, reservoirs, power systems, and water pipelines. The Las Vegas area is not in the same tectonic setting as Western Nevada's most active Walker Lane structures, but it still lies within the Basin and Range province, where faults and crustal extension shape the land. Earthquake hazard there is generally different from the hazard near northwestern Nevada, yet it is not absent. The concentration of people in Las Vegas changes the meaning of even moderate shaking. A large population means that many structures experience the same event at once. Tall buildings, older unreinforced structures, bridges, water lines, and transportation routes all respond according to their design, age, materials, and local ground conditions. The valley floor contains sediments that vary in thickness and stiffness. These materials can affect shaking patterns across the basin. A single earthquake may be felt differently from one neighborhood to another. Between these major urban centers, smaller towns and corridors also matter. Highways cross long valleys and mountain passes. Interstate routes connect Nevada to California, Oregon, Idaho, Utah, and Arizona. Rail lines, fuel pipelines, electrical transmission lines, fiber communication routes, and water systems follow paths selected for practical access rather than tectonic quiet. They often run along valley floors, across alluvial fans, and through narrow gaps between ranges. These corridors can be exposed to fault rupture, landslides, rockfall, liquefaction in wet sediments, or shaking damage, depending on local conditions. Liquefaction is a process in which saturated loose sediment temporarily loses strength during shaking. It requires water and suitable grain conditions, so it does not occur everywhere in Nevada's dry basins, where shallow groundwater exists, such as near rivers, wetlands, reservoirs, or irrigated ground. The possibility becomes more relevant. The process can damage foundations, roads, buried pipes, and embankments. Scientists and engineers evaluate it through soil studies, groundwater data, and expected shaking levels. Nevada's mining and energy systems add another layer of exposure. Mines, processing facilities, geothermal plants, solar installations, and transmission lines may lie far from dense cities, but still support regional economies and services. Some are located in seismically active terrain because mineral and geothermal resources often occur where the crust has been fractured and altered by heat and fluids. The relation is not simple. An industrial presence does not automatically mean high earthquake danger. Still, the overlap between useful resources and active geology requires careful monitoring and engineering. Modern building codes reduce risk by requiring structures to resist expected levels of shaking. They do not remove risk completely. Codes change over time as science improves and as damaging earthquakes reveal weaknesses. Older buildings may not meet current standards. Retrofitting can strengthen them, but it takes planning, funding, and public attention. The difference between hazard and disaster often depends on preparation, construction quality, emergency planning, and the resilience of lifelines. Earthquake risk around Nevada's urban edges also depends on time. A fault may remain quiet through decades of rapid growth. During that quiet period, homes, schools, roads, and businesses spread across the basin. The absence of recent damaging shaking can make risk feel remote. Yet geologic evidence may show that the surrounding faults have moved repeatedly over longer spans of time. Human memory is short compared with fault behavior. In this outer human layer, Migrating earthquakes become important not because every moving cluster leads to a large event, but because they reveal that the crust beneath populated corridors is active and changing. Small earthquakes can help scientists map hidden faults and identify regions where stress is being released. They can also remind planners that seismic hazard is distributed across a living landscape, the calm surface of a city street, a desert highway, or a mountainfront neighborhood rest within the same slow tectonic system that shapes Nevada's ranges and basins. Nevada's written earthquake record is short when compared with the age of its faults. The crust has been moving for millions of years, but careful human records cover only a small part of that time. This difference matters because a quiet century does not describe the full behavior of a fault system. The land may store evidence of many older earthquakes in scarps, displaced sediments, uplifted surfaces, and broken ground, while written accounts preserve only the events noticed by people and later measured by instruments. Before widespread settlement and scientific monitoring, earthquakes in Nevada were recorded unevenly. Strong shaking near a town, mining camp, rail line, or ranch might enter newspapers, diaries, or official reports. Shaking in remote basins could pass with little notice. A large event in an empty valley might leave surface rupture but few written descriptions. This makes the early record incomplete. It still provides useful information, especially where reports describe intensity, damage, landslides, ground cracks, or changes in springs. The late 19th and early 20th centuries brought more settlement, mining activity, rail travel, and communication across the state. More people meant more observations. Reports of shaking became easier to collect, and damaged structures gave scientists clues about earthquake strength. Still, the precision was limited. Before modern instruments, earthquake locations and magnitudes were estimated from felt reports and damage patterns. Magnitude is a measure of earthquake size based on the energy released. Intensity describes the shaking effects at a specific place. A single earthquake has one magnitude but many intensities across different locations. Nevada's historical record includes several large earthquakes that shape the scientific understanding of the region. In the early 20th century, strong earthquakes occurred in the western and central parts of the state. Some produced long surface ruptures across valleys and mountain fronts. These events showed that faults within the basin and range can release large amounts of strain suddenly. They also showed that dangerous earthquakes are not limited to coastal plate boundaries. One of the most important historic sequences occurred near Pleasant Valley in north-central Nevada. The earthquake there in the early 20th century produced extensive surface rupture along the range front. The ground broke across a long distance, and scarps formed where one side of the fault moved relative to the other. Because the region was sparsely populated, damage to buildings was limited compared with what a similar event might cause near a modern city. The geologic evidence, however, was clear. The earthquake demonstrated the capacity of Nevada faults to produce major rupture. Other significant events occurred in the Cedar Mountain and Dixie Valley areas during the 20th century. These earthquakes also produced surface deformation and strong shaking. They helped establish Nevada as one of the most active seismic regions in the continental United States. Scientists studied the ruptures to understand how normal faults move. A normal fault is a fault where the hanging side moves downward relative to the other side during extension. This motion fits the broader basin and range setting, where the crust is being stretched. The historical record also includes earthquake swarms and sequences that did not always produce one dominant main shock. A main shock is the largest earthquake in a sequence. In some parts of Nevada, Many small to moderate earthquakes occur close together in time and space. These swarms may continue for days, months, or longer. They are important because they reveal active structures that may not have produced recent large ruptures. They also show that seismic activity can move through a region rather than staying fixed at one point. As instruments improved, the record changed in character. Seismometers allowed scientists to detect smaller earthquakes and determine their locations more accurately. Early instrument networks were sparse, so small events were still missed in remote areas. Over time, more stations were installed. Each new station lowered the size of earthquakes that could be detected and improved the ability to identify clusters. This created the appearance of increasing activity in some records, even when part of the increase came from better observation. The historical record must therefore be read carefully. A modern catalogue contains many more small earthquakes than an older catalogue because instruments are more sensitive. This does not always mean the Earth has become more active. It means that scientists can now hear weaker motions. For larger earthquakes, the record is more complete, because strong shaking is noticed over wide areas. Even then, uncertainty remains for events in remote regions and for older periods. Geologists extend the record by studying paleoseismology, the science of ancient earthquakes preserved in the ground. They dig trenches across faults to examine layers of sediment that have been broken or displaced. A trench can reveal several past earthquakes if each event disturbed the layers in a recognizable way. Organic material or minerals within the layers may be dated to estimate when movement occurred. These studies show that many Nevada faults have longer earthquake histories than written records reveal. The timing between large earthquakes on a fault can be irregular. Some faults may rupture every few thousand years on average, but the actual intervals can vary widely. A fault that has not moved during recorded history may still be capable of a future earthquake. Another fault that produced a large event recently may continue generating smaller aftershocks or swarms. Observations indicate that recurrence estimates contain uncertainty because the record is incomplete and fault behavior is complex. Historical damage patterns also depend on where people lived at the time. A large earthquake in a rural basin may produce spectacular ground rupture but little economic loss. A smaller earthquake near a city may cause more disruption. As Nevada's population has grown, especially in the Reno, Carson City, and Las Vegas regions, the potential consequences of shaking have changed. The same geologic event can carry different human impact depending on the built environment above it. The record of migrating earthquakes fits into this historical frame. Earlier observers could feel bursts of shaking but could not map the detailed movement of small events through the crust. Modern catalogues reveal sequences that would once have been invisible. Some swarms trace patterns across faults and basins. Some remain confined. Some fade without larger rupture. The historical record shows that Nevada has produced damaging earthquakes, while modern monitoring shows that the crust also releases energy through many smaller, moving sequences. This layer of memory is uneven but valuable. Written accounts preserve human experience. Instrument catalogues preserve measured vibrations. Trenches preserve ancient ground movement. Fault scarps preserve the visible mark of rupture. Together, they show that Nevada's seismic present is part of a much longer record, one that is incomplete but clear enough to show continuing hazard beneath a landscape that often appears still. Modern seismic networks form a quiet listening layer across Nevada and the surrounding region. They do not prevent earthquakes, and they do not make faults move. They record motion as it passes through the ground. With enough instruments, scientists can locate small earthquakes, measure their size, and follow changing patterns through time. This careful listening turns scattered vibrations into maps of active crust. A seismometer is an instrument that measures ground motion. It may detect shaking from a nearby small earthquake, a distant large earthquake, a quarry blast, a storm-driven vibration, or human activity. The instrument records waves that travel through the Earth after a sudden release of energy. Earthquake waves arrive in different forms. Some travel through the body of the Earth. Some travel along the surface. Their arrival times help scientists estimate where the earthquake began. The point where rupture starts underground is called the hypocenter. The point directly above it at the surface is called the epicenter. In ordinary speech, the epicenter is often treated as the earthquake location, but the depth also matters. A shallow earthquake close to a city can produce stronger local shaking than a deeper event of similar size. In Nevada, many earthquakes occur within the brittle upper crust, where rock is cool enough to break rather than flow. To locate an earthquake, a network needs several stations. When an earthquake occurs, waves reach the nearest station first and more distant stations later. The time differences allow scientists to calculate the origin time and position. The more stations that record the event, and the better their distribution around it, the more precise the location can become. In remote basins with fewer stations, uncertainty may be larger. In well-instrumented regions, even small clusters can be mapped in detail. Nevada benefits from regional monitoring that includes university networks, national systems, temporary deployments, and data shared across state boundaries. Earthquakes do not follow political borders, so networks must consider the wider tectonic region. A sequence in western Nevada may relate to faults extending toward California. A sequence in eastern Nevada may be recorded by stations in Utah or Idaho. Combining data improves the view of active structures. Magnitude estimates also depend on instruments. Magnitude describes the size of an earthquake using measured wave amplitudes and other source properties. Small events may have negative or very low magnitudes if they are detectable only by sensitive instruments. Moderate events may be felt by people. Large events release far more energy and can produce damaging shaking over broad areas. The scale is logarithmic, meaning each step represents a large change in measured amplitude and energy. For the narrator's steady purpose, the important point is simple. Magnitude is a measure of size, not a direct measure of damage. Damage depends on many other conditions: distance from the fault, earthquake depth, rupture direction, local soil, building design, and duration of shaking all matter. A seismometer records ground motion at its site. A network of seismometers shows how shaking varies across space. Strong motion instruments are designed to record larger shaking without being overwhelmed. Their records help engineers understand what buildings and bridges experience during earthquakes. For migrating earthquake sequences, accurate locations are especially important. A cluster may appear to move across a map only because early locations are uncertain. Scientists must test whether the apparent migration is real. They use improved methods, compare waveforms, refine velocity models, and sometimes relocate events relative to one another. A velocity model describes how fast seismic waves travel through different rocks. If that model is wrong, earthquake depths and positions may shift. Careful analysis reduces these errors. When many small earthquakes occur close together, their waveforms may look similar. A waveform is the recorded shape of ground motion through time. Similar waveforms suggest that earthquakes occurred near one another and slipped in similar ways. By comparing these records, scientists can sharpen the relative locations of events. This is useful in swarms, where tiny changes in position may reveal whether activity follows a fault plane, spreads through a volume of fractured rock, or moves along several connected structures. Time is as important as position. A catalogue of earthquakes records when each event occurs. If activity begins in one part of a swarm and then appears farther away days or weeks later, scientists examine the pattern. They compare the migration rate with possible processes. Slow movement may be consistent with fluid pressure diffusion in some cases. Faster triggering may suggest stress transfer through elastic rock. Observations can support one explanation more than another. But uncertainty often remains because several processes may operate together. Seismic networks also record aftershocks. Aftershocks are smaller earthquakes that follow a larger event as the crust adjusts to change stress. They usually cluster around the rupture area, but their distribution may outline parts of the fault that slipped or nearby faults that were disturbed. In Nevada, aftershock patterns from historic and modern events help scientists understand fault geometry. They can show dipping planes beneath range fronts or more complex structures beneath basins. Not every earthquake sequence has a clear main shock and aftershock pattern. Some swarms rise and fall without one dominant event. The number of earthquakes may increase gradually, peak, and decline. The locations may migrate, expand, or pulse in separate bursts. Seismic networks make these behaviors visible. Without instruments, such swarms might be known only as occasional felt shaking or not known at all. The data must be filtered and interpreted with care. Instruments can record noise from wind, traffic, mining, construction, and other surface sources. Analysts and automated systems distinguish earthquakes from non-earthquake signals by their wave shapes, arrival patterns, and station coverage. Automated catalogues are useful for rapid detection, but human review and advanced processing remain important for research quality results. As networks grow denser, scientists detect more small earthquakes. This improves understanding but also changes public perception. A map filled with tiny events may look alarming, though many are too weak to affect people. The increase in visible seismicity may reflect improved detection rather than a sudden change in hazard. Clear communication is part of the scientific task. Small earthquakes show that faults and fractures are active, but they do not automatically mean a larger earthquake is imminent. In Nevada, the listening network connects the quiet surface to the moving crust below. Each sensor adds a point of attention. Each recorded wave adds a small piece of information. Over time, thousands of small signals reveal patterns that no single event can show. Migrating earthquakes become visible as ordered motion within a cloud of points. Faults hidden beneath sediment begin to take shape. The outer human record becomes a measured scientific record, built from steady instruments placed across a restless but slowly moving land. Migrating earthquake sequences appear when many small earthquakes form a pattern that changes position through time. In Nevada, these sequences are often studied as swarms, which are groups of earthquakes that occur close together without always having one clear largest event at the beginning. A swarm may begin in one small area of crust, then spread into nearby rock, shift along a fault, or appear in separate pulses. The movement is not like a visible wave across the desert surface. It is pattern found in the timing and locations of many small ruptures underground. The word migration describes the observed movement of earthquake activity, not the movement of each individual earthquake. Each earthquake begins and ends quickly. What migrates is the active zone, the part of the crust where new events continue to occur. Scientists identify this motion by placing many earthquake locations on a map and arranging them by time. Early events may cluster in one place. Later events may appear farther away, if the change is steady enough. The sequence can be described as migrating. Nevada's crust is well suited for such patterns because it is fractured, extended, heated in some areas, and crossed by many fault systems. The faults do not form one simple surface. They branch, overlap, bend, and sometimes fade into zones of smaller fractures. When stress or pressure changes in one part of this network, nearby parts may respond. The response may be a few tiny earthquakes, a long swarm, or a larger rupture. Observations indicate that migration can occur in several different ways, and it remains uncertain which process dominates in every sequence. Some migrating swarms move slowly enough that fluid pressure is considered a possible influence. Fluids in this context usually mean water or brines held in pores and fractures within rock. Pore pressure is the pressure of fluid inside small spaces. When pore pressure increases, it can reduce the effective clamping force holding a fault closed. A fault that is already close to failure may then slip in a small earthquake. If pressure changes move outward through connected fractures, earthquake activity may also appear to move. This process is called diffusion, meaning gradual spreading through a medium. Other sequences may move too quickly, too irregularly, or across structures where fluid movement alone does not explain the pattern. In those cases, stress transfer may be more important. When one earthquake slips, it changes the stress in the surrounding crust. Some nearby patches become slightly more stressed, while others become less stressed. If a nearby patch is already near failure, even a small stress change can help trigger another earthquake. A chain of such changes can make activity appear to migrate through a fault network. A migrating sequence may also reflect aseismic slip. Aseismic slip means fault movement that occurs slowly without producing strong seismic waves. If part of a fault creeps quietly, it can load nearby locked patches. These locked patches may then break as small earthquakes. The earthquakes outline the edge or path of the silent slip rather than the entire moving area. In some regions, observations support this process. In others, the data are not sufficient to confirm it. The shape of a migration pattern depends on the structure of the crust. If earthquakes line up along a dipping plane, they may show movement along a fault surface. If they spread through a broad cloud, they may indicate a fractured volume or several hidden faults. If they jump between separated clusters, they may be responding to stress changes across a larger network. The same map can contain several behaviors, so scientists avoid assuming a single cause from appearance alone. Depth adds another dimension. A sequence may migrate horizontally across a basin, vertically through the crust, or both. In Nevada, many earthquakes occur within the brittle upper crust, where rock breaks under stress. The exact depth range varies by region, temperature, rock type, and local conditions. Shallow swarms may be influenced by groundwater systems or geothermal activity in some places. Deeper swarms may reflect tectonic stress within stronger rock. Observations indicate that depth patterns can help distinguish possible causes, but they do not always provide a complete answer. Timescales vary widely. Some swarms unfold over hours or days, others continue for months. A few regions may show repeated sequences over years. The rate of migration can be compared with known physical processes. Slow outward spreading may resemble pressure diffusion. More sudden movement may resemble stress triggering. Irregular bursts may suggest that the crust contains barriers, weak zones, or changes in permeability. Permeability means the ability of rock to let fluids pass through connected spaces. The size distribution of earthquakes also matters. Many swarms contain numerous tiny events and only a few moderate ones. Some sequences include a main shock that is followed by aftershocks, while others do not. When there is no clear main shock, the swarm may feel less orderly to observers, but the data can still reveal structure. The number of events, their spacing, their depths, and their magnitudes all help define the process. Migrating earthquakes are not automatically a warning of a much larger earthquake. Most swarms end without producing damaging events. However, they deserve attention because they show where the crust is actively responding to changing conditions. A swarm near a mapped fault may clarify that the fault or its surrounding fractures are active. A swarm in a basin may reveal a hidden structure. A migrating pattern near infrastructure may prompt closer monitoring, especially if events become larger or shallower. Scientists treat these sequences with measured caution. They can say where activity is occurring and how it is changing. They can compare the pattern with physical models. They can estimate whether the sequence resembles past swarms that faded or sequences that developed into larger events. They cannot predict with certainty that a specific swarm will stop or grow. Earthquake systems are sensitive to conditions that are partly hidden below the surface. The value of studying migration lies in detail. A single earthquake gives one point of information. A moving swarm gives many points arranged through space and time. It reveals how fractures connect, how stress may move, how fluids may influence faults, and where the crust is close enough to failure to respond. In Nevada, these patterns turn the deep fault network from a static map into a changing process. The desert surface remains quiet, but beneath it, small ruptures trace the slow adjustment of broken rock. Fault segment geometry describes the shape and arrangement of the broken surfaces where earthquakes can occur. In Nevada, this geometry is rarely simple. Faults may appear on maps as lines, but beneath the surface they are planes, curves, branches, steps, and zones of crushed rock. Some continue for many kilometers, others end, bend, or disappear under basin sediment. A migrating earthquake sequence often follows these hidden shapes, so understanding the geometry is essential to understanding the motion. A fault segment is a section of a larger fault system that behaves partly as its own unit. It may be separated from neighboring sections by a bend, a gap, a change in rock type, or a crossing structure. During an earthquake, rupture may remain within one segment or pass into another. The boundary does not act as an absolute wall. It acts as a place where rupture behavior can change. Sometimes movement slows or stops there. Sometimes it continues through. In the basin and range, many faults are normal faults formed by crustal extension. These faults usually dip into the earth, meaning they slope downward beneath one side of the range or basin. At the surface, a normal fault may trace the front of a mountain range, while at depth it angles beneath the valley. When it slips, the hanging side moves downward. Over many events, this motion helps create high ranges and low basins. Yet the fault surface may not be smooth. It may curve, flatten, branch, or connect with older structures. Strike-slip faults, common in parts of the Walker Lane, have different geometry. Their main motion is horizontal. They may run across valleys, cut through mountain blocks, or form long zones of sheared rock. Where a strike-slip fault bends, the crust may be compressed or pulled apart. Compression can raise small ridges. Extension can open small basins. These bends and steps influence where earthquakes begin and how they move. The places where faults overlap are especially important. One fault may end near another, leaving a step between them. If the step is small and favorably oriented, rupture or stress changes may transfer across it. If the step is wide or poorly aligned, it may slow or stop rupture. Earthquake swarms can move through such regions in a staggered pattern, appearing first on one strand and later on another. The map may look scattered, but the pattern can reflect the underlying geometry. Faults also interact at depth. A surface trace may not show the full structure below. In some basins, several small faults near the surface may merge into a broader zone deeper in the crust. In other places, a single mapped fault may split downward into multiple surfaces. Earthquake locations can reveal these arrangements when they form planes or clusters. A line of epicenters on a surface map may hide a dipping sheet of hypercenters below. The depth of a fault segment affects how it participates in earthquakes. Shallow parts may break the surface during large events. Deeper parts may produce earthquakes without visible rupture above. Some shallow fault strands may be weak, filled with broken material, or partly covered by sediment. Some deeper sections may be stronger and more capable of storing elastic strain. These differences influence where small earthquakes cluster and where larger slip may occur. Rock type can also guide fault geometry. Nevada contains volcanic rocks, sedimentary layers, crystalline rocks, and altered zones shaped by heat and fluids. Each rock type responds differently to stress. A fault may follow a weak layer, cut across older bedding, or reactivate an ancient fracture. Reactivation means an older structure moves again under a new stress field. Many faults in Western North America reflect long histories, where old weaknesses are reused in new tectonic settings. At the surface, geometry is read through landforms. A straight mountain front may mark a long fault segment. A sudden bend in the range may mark a change in fault direction. A basin shaped like a narrow pull-apart depression may indicate sideways motion along stepping strike-slip faults. A line of springs may reveal a fracture zone that channels groundwater. These clues are useful, but they do not replace subsurface data, erosion, sediment cover, and younger deposits can hide or soften the true fault pattern. Migrating earthquakes often make hidden geometry clearer. If a swarm begins near one fault trace and then moves toward another, scientists examine whether the two are connected underground. If events align along a plane that dips beneath a basin, the swarm may reveal the active surface of a buried normal fault. If events form several short lineations, they may outline a network of smaller fractures rather than one main fault. The details matter because different structures carry different hazard implications. A segment boundary may affect the possible size of an earthquake. A rupture limited to a short segment has less length available than one that continues across several segments. Longer ruptures can produce larger earthquakes, though size also depends on width, slip amount, and other conditions. Scientists therefore map segment boundaries carefully. They do not assume that every boundary will stop rupture, but they treat each boundary as a feature that can influence behavior. Fault geometry also controls how stress concentrates. At the tips of faults, stress may increase in nearby rock. At bends, stress may gather in zones of compression or extension. Where faults intersect, the pattern becomes more complex. These stress concentrations can encourage small earthquakes, especially when the rock is already close to failure. A migrating sequence may move toward a fault tip, around a bend, or through an intersection as stress and pressure conditions change. The uncertainty in fault geometry remains significant in many parts of Nevada. Large areas are covered by young basin sediment. Some faults have not ruptured during recorded history. Some small earthquakes occur on structures that have no clear surface expression. Geologists combine field mapping, seismic records, gravity data, magnetic data, satellite measurements, and trench studies to improve the picture. Each method sees a different part of the system. For communities and infrastructure, the geometry matters because shaking and rupture depend on where faults lie and how they connect. A hidden fault beneath a basin may be more relevant to a town than a visible fault in a distant range. A segmented fault system may produce several moderate earthquakes or, under some conditions, a longer rupture. Observations can define possibilities, while uncertainty remains in exact timing and rupture path. In this inner structural layer, Nevada's migrating earthquakes become tracers. They move through faults shaped by extension, shear, old weakness, rock variation, and buried connections. Their paths do not wander randomly. They follow the architecture of fractured crust, sometimes revealing it more clearly than the surface can. The geometry of faults gives the migrating sequences their channels, their barriers, and their quiet turns through the broken stone beneath the basins. Stress transfer describes the way one movement in the crust changes the forces around it. In Nevada's fault networks, this process helps explain why earthquakes can cluster, shift, or migrate without requiring one single fault to rupture all at once. The crust is already under long-term tectonic strain. A small earthquake does not create that broad strain. It changes a local part of it, adding stress to some nearby areas and reducing stress in others. Stress is force acting within rock. A fault slips when the stress trying to move it becomes large enough to overcome the resistance holding it in place. That resistance depends on friction, rock strength, fluid pressure, and the orientation of the fault. Many faults in Nevada are already loaded by slow regional extension and shear. They may remain locked for long periods, then slip when conditions change slightly. Stress transfer is one way those slight changes occur. When an earthquake happens, two sides of a fault move. The movement releases stress on the part that slips, but the surrounding crust must adjust. Some patches near the rupture become more likely to fail because the stress on them increases. Other patches become less likely to fail because stress decreases or the fault is pressed more tightly closed. This pattern depends on the size of the earthquake, the direction of slip, the shape of the fault, and the orientation of nearby faults. The changes may be small, but faults close to failure can respond to small changes. This is why aftershocks often occur near a larger earthquake. The main rupture alters the stress field, and nearby patches adjust. Some aftershocks occur within minutes. Others occur over days, months, or years. In a complex region like Nevada, the aftershock zone may outline the fault that slipped, nearby branches, or hidden structures beneath basins. Stress transfer can also occur between earthquakes of similar size. A swarm may not contain a clear dominant event. Instead, each small slip changes the forces around it a little. The next event may occur where the new stress is favorable. Over time, this can make the active zone appear to move. The movement may be irregular because the crust is not uniform. Some faults are well oriented for the present stress field. Others are not. Some patches are strong. Others are weak or affected by fluids. Scientists often distinguish between static and dynamic stress transfer. Static stress transfer refers to the lasting change in stress after a fault has slipped and the crust has settled into a new balance. Dynamic stress transfer refers to the passing seismic waves that briefly shake distant faults as they travel through the earth. A distant large earthquake can send waves across Nevada and trigger small events in sensitive regions, especially geothermal areas or fault zones already near failure. Such triggering does not mean the distant earthquake caused the long-term tectonic stress. It means the passing waves disturbed a system that was already close to moving. In Nevada, both kinds of transfer may be relevant in different sequences. A local earthquake can change static stress on nearby fault patches. A distant major earthquake can produce transient shaking that affects swarms in responsive areas. Observations indicate that some geothermal and volcanic regions in the western United States can show triggered seismicity after large distant earthquakes. It remains uncertain for any particular sequence until timing, location, wave passage, and local conditions are examined together. Stress transfer is often studied with models. A model is a simplified representation of a physical system. Scientists estimate the fault orientation, slip direction, earthquake size, and surrounding rock properties. They calculate which nearby faults should receive an increase or decrease in failure stress. These calculations can be compared with observed aftershocks or migrating clusters. A good match supports the interpretation, but the result is never a perfect image of the subsurface. Faults may be unmapped, rock properties may vary, and fluid pressure may change in ways that are not fully known. The role of fault orientation is central. A stress change that encourages slip on one fault may discourage slip on another fault nearby. This is because each fault sits at its own angle within the stress field. Normal faults, strike-slip faults, and oblique faults respond differently depending on how they face the forces around them. A migrating sequence may seem to bypass one structure and activate another, because the second structure is more favorably oriented for the stress change. Distance also matters. Static stress changes are usually strongest near the rupture and weaken with distance. Dynamic waves can travel much farther, though their effects are brief. A small earthquake generally affects only a small volume strongly. A larger earthquake can alter stress over a broader region. In Nevada's distributed fault systems, even modest events may influence nearby branches if they are close enough and already near failure. Stress transfer does not provide simple prediction. An increase in calculated stress does not guarantee an earthquake. A decrease does not guarantee safety. The state of each fault before the stress change is only partly known. A fault that receives added stress may remain locked if it was far from failure. A fault that receives a small change may slip if it was already close to failure. This uncertainty is one reason earthquake forecasting remains probabilistic rather than exact. Migrating sequences are useful because they let scientists observe stress adjustment in action. If earthquakes move from one end of a cluster to another after a larger event, researchers can test whether the movement follows zones of increased stress. If the activity spreads in a pattern inconsistent with stress transfer alone, they consider other processes such as fluid pressure or slow slip. The interpretation becomes stronger when several lines of evidence agree. In the deeper view of Nevada's crust, stress transfer connects separate earthquakes into a broader pattern. A fault does not act alone. It belongs to a network of fractures embedded in an elastic crust that bends, stretches, and rebounds. Elastic means that rock can store strain and partly recover shape after stress changes, though it may also break when limits are exceeded. Every small slip slightly rearranges the forces around it. The effect is quiet until it is measured. No visible signal crosses the desert when a small earthquake changes stress on a buried fault. The surface may remain unchanged. Instruments record the shaking, and later events reveal whether nearby parts of the crust respond. In this way, stress transfer becomes a hidden conversation within rock, not in words, but in force, friction, and motion. Nevada's migrating earthquakes show parts of that conversation as clusters shift through faults, already shaped by slow regional strain. Fluids move quietly through parts of Nevada's crust. Most remain far below the surface, traveling through pores, fractures, and permeable rock layers that formed over long geologic time. In some regions, These fluids carry heat upward from depth. In others, they remain cool groundwater circulating through sediment and broken stone. Their movement is usually slow and hidden, but under certain conditions it may influence earthquake behavior, especially within migrating swarms. Rock deep underground is rarely completely solid in the ordinary sense. Even strong crystalline rock can contain fractures and microscopic spaces. Sedimentary layers may contain larger pore networks. Water enters these spaces through rainfall, snowmelt, ancient trapped fluids, or deeper circulation paths connected to faults. The pressure inside these pores matters because it affects how tightly rock surfaces press together. A fault remains locked partly because friction resists sliding. That resistance depends on the force pressing the two sides together. If fluid pressure within the fault zone increases, the effective clamping force decreases. A fault that was stable may then move more easily. In some cases, only a small increase in pore pressure is needed if the fault is already close to failure from tectonic stress. This process does not create the regional tectonic forces acting on Nevada. The broader extension of the basin and range and the shear of the Walker Lane come from plate motion and crustal deformation. Fluids instead act as modifiers within the existing stress field. They can change when and where small ruptures occur. Observations indicate that fluids are important in some swarms, though not all sequences require fluid involvement. Geothermal regions provide some of the clearest examples of fluid-rich crust. Nevada contains many geothermal systems because the crust is relatively warm and fractured in certain areas. Heat from deeper rock warms underground water, which then rises through faults and permeable zones. At the surface, this circulation may appear as hot springs, altered minerals, steam fields, or warm groundwater. At depth, the moving fluids interact with stressed rock. Earthquake swarms near geothermal areas often display characteristics that attract scientific attention. The earthquakes may cluster tightly, migrate gradually, and continue for extended periods without one dominant main shock. In some sequences, the migration speed resembles diffusion, the slow, outward spread expected when pressure changes move through connected fractures. Scientists compare the observed migration rates with theoretical models of fluid flow through rock. Permeability strongly influences these patterns. Permeability describes how easily fluids move through a material. A heavily fractured fault zone may allow rapid fluid movement in one direction, while blocking it in another. Mineral deposits conceal fractures over time, reducing permeability. Later stress or earthquakes may reopen pathways. The crust therefore behaves as a changing hydraulic system, rather than a fixed network of pipes. Temperature also affects rock behavior. Warmer rock tends to deform more easily at depth, while cooler rock remains brittle and more likely to fracture suddenly. Nevada's geothermal regions often sit near the transition between these conditions. The upper crust remains brittle enough for earthquakes, while heat and fluids alter friction and pressure conditions. This combination can produce persistent microseismicity, meaning many very small earthquakes recorded only by instruments. Scientists study these regions using seismic networks, temperature measurements, fluid chemistry, satellite observations, and subsurface imaging. Earthquake locations may outline active fractures carrying fluids upward. Changes in seismic activity may coincide with pressure changes or shifts in groundwater systems. However, interpreting the exact relation between fluids and earthquakes remains difficult because many variables interact at once. One important uncertainty involves causation. A migrating swarm and fluid movement may occur together, but proving that pressure changes directly triggered each earthquake is challenging. The crust contains pre-existing faults already stressed by tectonic forces. Fluids may weaken those faults, but stress transfer from earlier earthquakes may also contribute. In many sequences, researchers conclude that both effects likely operate together. The movement of fluids can also be influenced by earthquakes themselves. When faults slip, fractures may open or close. This changes permeability and redirects underground flow. Springs may change discharge after strong earthquakes. Water levels in wells may rise or fall. In rare cases, new seepage paths appear temporarily. These changes show that the relation between fluids and earthquakes is two-directional. Fluids can influence faults, and fault movement can reorganize fluids. The scale of fluid influence varies greatly. In some regions, the effect may be confined to a small geothermal field. In others, pressure changes may spread across broader fracture networks. The migration rate offers clues. Slow outward progression over weeks or months can resemble pressure diffusion through rock. Faster jumps across faults may indicate that stress transfer is more important than direct fluid movement. The observed pattern helps narrow possibilities but rarely removes uncertainty completely. Fluid-rich fault zones may also produce earthquakes at relatively low stress levels because elevated pore pressure reduces frictional resistance. This does not necessarily mean large earthquakes become inevitable. Many fluid-influenced swarms remain small. The energy release may occur through numerous minor events rather than one major rupture. Scientists therefore distinguish between seismic activity and seismic hazard. Increased earthquake counts do not automatically imply increased probability of a destructive event. Nevada's dry surface can make the presence of underground water seem surprising. Yet the deep crust operates under very different conditions from the desert above. Water circulates far below dry valleys and gravel plains. Heat rises from depth through fractured rock. Chemical reactions alter minerals along fault zones. These processes continue quietly beneath landscapes that appear empty and still. Fluid pressure changes are often invisible at the surface. A migrating swarm may provide the first sign that pressure conditions are evolving underground. Instruments detect tiny earthquakes tracing pathways through the crust. Over time, the sequence may outline a fault zone, a geothermal reservoir, or a connected fracture network. In this way, seismicity becomes a kind of indirect imaging system, revealing movement in places humans cannot reach directly. The deeper understanding remains incomplete. Scientists know that fluids can influence earthquake timing and migration under some conditions. They know that pore pressure reduces effective fault strength. They observe swarms whose behavior resembles diffusion through fractured rock. Yet each sequence contains its own geometry, stress field, rock properties, and thermal structure. Nevada's migrating earthquakes therefore remain a subject of continuing study, where fluids form one important layer within a broader tectonic system of strain, fracture, and slow crustal motion. Geothermal and human activity form a narrower layer within Nevada's earthquake story, where natural heat, useful energy, engineered systems, and small seismic events meet in the fractured crust. Nevada has many geothermal fields because parts of the state contain warm rock, active faults, and groundwater pathways close enough to the surface for heat to be reached. These places are not separate from the broader tectonic setting. They occur within the same stretched and broken province that shapes the valleys and mountain ranges. A geothermal system begins with heat. The heat may come from warm crust, past volcanic activity, or the general upward flow of energy from deeper earth. Water moves through fractures, absorbs heat, and rises through permeable zones. Permeable rock allows fluids to pass through connected openings. Faults can create these openings by breaking and crushing rock. They can also seal pathways when minerals fill cracks. This makes every geothermal field a changing underground system rather than a simple reservoir. Human use of geothermal energy depends on reaching these hot fluids or hot rocks. Wells are drilled into suitable zones. Hot water or steam is brought upward, used to produce electricity or heat, and often returned underground through injection wells. Injection means placing fluid back into the subsurface. This helps maintain pressure and reduce waste, but it also changes local pressure conditions, where faults are already stressed. These pressure changes can sometimes encourage small earthquakes. Induced seismicity is earthquake activity caused or influenced by human actions. In geothermal settings, it is usually associated with changes in fluid pressure, temperature, or stress near wells. Most induced events are small. Many are detected only by instruments. Some can be felt locally. A smaller number worldwide have caused public concern or damage. Nevada's geothermal fields are monitored because the state contains both active tectonic faults and energy operations that interact with fractured rock. It is important to separate natural tectonic hazard from operation-related seismicity. Nevada would have earthquakes without geothermal development. The crust is already extending, shearing, and storing strain. Geothermal operations can affect local conditions in specific fields, especially near wells, but they do not create the broad plate-driven forces that shape the state. When earthquake activity occurs near a geothermal plant, scientists examine timing, location, depth, injection records, production records, and fault geometry before assigning a cause. Some geothermal fields produce steady background microseismicity. Microseismicity means very small earthquakes recorded by sensitive instruments. These events can help operators and scientists map fractures and understand how fluids move. A cluster of small earthquakes near an injection zone may show where pressure is spreading. A change in depth or direction may reveal a connected fault or a boundary in permeability. The same data that raise caution can also improve understanding. Enhanced geothermal systems add another layer of complexity. In these systems, engineers attempt to improve permeability in hot rock where natural fluid pathways are insufficient. This may involve injecting fluid under pressure to open existing fractures or create better flow between wells. Such stimulation can increase small earthquake activity because the process directly changes pressure and stress within fractured rock. The goal is controlled improvement of circulation. Not uncontrolled rupture, but uncertainty remains because the subsurface cannot be observed directly. Nevada's experience fits within a broader scientific consensus. Fluid injection can trigger earthquakes when it raises pore pressure on faults that are close to failure. The likelihood depends on injection volume, rate, pressure, rock permeability, fault orientation, distance to faults, and the existing stress field. No single factor explains every case. A small injection in a sensitive fault zone may matter more than a larger injection in less responsive rock. Careful site study and monitoring are therefore essential. Operators and regulators use monitoring systems to reduce risk. Seismic networks around geothermal sites can detect small events early. Pressure and flow data show how operations change underground conditions. Some projects use response plans that adjust injection or production if seismicity reaches certain levels. These plans do not eliminate uncertainty, but they provide a practical way to manage activity in real time. The approach is based on observation, adjustment, and caution. Other human activities in Nevada may also interact with seismic conditions, though their mechanisms differ. Mining changes the stress in rock near excavations and can produce small seismic events around underground workings. Reservoirs may alter loads and groundwater pressures in some settings. Construction, quarrying, and blasting produce vibrations that instruments must distinguish from earthquakes. These activities are generally local in scale compared with tectonic forces, but they can matter for monitoring and interpretation. The challenge for scientists is attribution. When a swarm occurs in an active tectonic region, it may be natural, induced, or influenced by both natural and human factors. The crust does not label its causes. Researchers rely on evidence. If earthquakes begin after a clear pressure change, occur near injection wells, align with known fluid pathways, and change when operations change, an operational influence becomes more likely. If activity occurs far from operations or follows regional tectonic patterns without operational timing, a natural explanation may be stronger. Public concern often grows when earthquakes occur near energy facilities, especially in populated or economically important areas. Clear communication matters. Small induced earthquakes are not the same as large regional earthquakes, but they are still meaningful. They can be felt, they can affect public trust, and they can reveal that a fault system is responsive. Scientific language must remain careful, because overstatement creates fear and understatement weakens preparedness. Geothermal energy also provides benefits. It can produce steady electricity with low surface emissions compared with fossil fuel systems. In Nevada, it forms part of a broader energy landscape that includes solar resources, mining, transmission corridors, and growing demand. The presence of seismic risk does not make geothermal use impossible. It makes site selection, engineering, monitoring, regulation, and public planning necessary. At the scale of migrating earthquakes, geothermal fields are valuable natural laboratories. They contain heat, fluid flow, fractured rock, and dense monitoring. Small earthquakes may trace pressure movement through the crust more clearly than in remote regions with fewer instruments. These observations help scientists understand processes that also occur naturally, including pore pressure change, fracture opening, fault weakness, and swarm migration. The inner lesson of this layer is measured and specific. Human activity can influence small earthquakes under certain conditions, especially where fluid pressure changes act on stressed faults. Nevada's larger seismic setting remains natural and tectonic. The two realities can overlap in geothermal areas, where heat draws industry into the same fractured ground that records ongoing crustal strain. The moving clusters beneath these fields are not simply industrial noise and not always purely natural background. They are signals from a shared space where engineered pressure, deep heat, flowing water, and ancient faults meet within the rock. The crustal depth zone beneath Nevada is the layer where most local earthquakes begin. It lies below the visible basins, below the buried sediments, below the mapped fault traces, and within rock that is cool and strong enough to break suddenly. This part of the earth is known as the brittle crust. Brittle means that rock can fracture when stress exceeds its strength. It may bend slightly and store strain, but when the limit is reached, it breaks or slips along an existing fault. In Nevada, many earthquakes occur within the upper to middle crust. The exact depth varies by region. Some events are shallow, only a few kilometers below the surface. Others begin deeper, where pressure is greater and the temperature is higher. The lower limit of ordinary earthquake activity depends on temperature, rock type, fluid pressure, strain rate, and mineral composition. Below that limit, rock tends to deform more slowly rather than rupture in sharp seismic events. Depth matters because it influences shaking at the surface. A shallow earthquake can send strong waves into nearby ground with little distance for the energy to spread. A deeper earthquake may be felt over a wider area, but its stronger surface shaking can be reduced by distance. The relationship is not simple, because magnitude, fault orientation, rupture direction, and local sediments also affect shaking. Still, depth remains one of the central measurements in understanding Nevada's seismic hazard. The brittle crust is not a uniform block. It contains layers, old faults, intrusions, fractures, altered zones, and buried basins. Some rocks formed in ancient oceans, some formed in volcanic eruptions, some cooled slowly underground as crystalline bodies. Some were buried, folded, heated, and lifted again. These different rocks now share the same regional stress field, but they do not respond in exactly the same way. Strong rocks may store strain for long periods. Weaker zones may slip more often in small events. At depth, pressure increases with the weight of overlying rock. This pressure tends to clamp fractures closed. At the same time, tectonic stress tries to move faults. Fluid pressure can partly counter the clamping force. Temperature changes the frictional behavior of minerals. The result is a narrow balance. A fault may remain locked for years, decades, or centuries, then slip when stress, pressure, or strength changes enough. Many migrating swarms occur within this balance, where small changes can activate nearby patches. Earthquake depth is measured indirectly. Seismometers record waves at the surface. Scientists estimate where the waves began by comparing arrival times at many stations and by using models of wave speed through the crust. If the station network is dense and surrounds the sequence, depth estimates can be more reliable. If stations are distant or unevenly distributed, depth uncertainty grows. This is especially important in Nevada's remote basins, where sparse coverage can make small earthquakes harder to place precisely. Improved depth locations can reveal the shape of active faults. A cluster of earthquakes may form a dipping plane beneath a mountain front. The plane may mark a normal fault extending downward below the valley. Another cluster may form a near-vertical pattern, more consistent with strike-slip motion. Some swarms form clouds rather than planes, suggesting many small fractures or a complex fault zone. The depth pattern often gives more information than the surface map alone. Within the brittle crust, fault surfaces are rough. They contain locked patches, crushed rock, mineral-filled seams, and small bends. A fault does not usually slip evenly across its entire surface. Some areas resist movement more strongly. These stronger patches are sometimes called asperities. When stress builds, an asperity may hold until it fails suddenly. Smaller earthquakes may occur around it, or a larger rupture may break through it. The distribution of strong and weak patches is mostly hidden from direct observation. Migrating earthquake sequences can move along these rough surfaces. Activity may begin where a weak patch slips, then advance toward neighboring patches that are close to failure. It may stop where the fault becomes stronger, where geometry changes, or where stress is reduced. It may shift upward, downward, or sideways along connected fractures. The movement is not a smooth front through empty space. It is a sequence of small failures within a broken and uneven medium. The temperature structure of Nevada's crust is important in this depth zone. In regions with high heat flow, the brittle layer may be thinner because warmer rock at depth becomes less likely to break suddenly. In cooler regions, earthquakes may extend deeper. Geothermal areas can therefore show shallow, active seismicity related to heat and fluids, while other regions may produce deeper tectonic events. Observations support these broad patterns, though local variation is common. Rock at earthquake depth is also affected by chemical alteration. Fluids moving through fractures can change minerals, deposit silica or carbonates, weaken surfaces, or seal cracks. A sealed crack may later break again under stress. A weak clay-rich zone may slide more easily than surrounding rock. These mineral changes are slow, but they influence how faults behave during later earthquakes. The crust carries memory not only in its shapes, but also in its altered materials. Seismic waves generated at depth pass through this layered crust before reaching the surface. Their paths bend, reflect, scatter, and slow depending on the rocks they cross. A wave moving through hard, crystalline rock behaves differently from one entering a deep sedimentary basin. This is why an earthquake of the same magnitude and depth can produce different shaking patterns in different valleys. The source lies in the crustal depth zone, but the final surface motion depends on the whole path upward. The brittle crust also contains the boundary between silent strain and audible rupture. Slow deformation may occur without earthquakes on some faults or deeper surfaces. Nearby locked areas may respond with small earthquakes. This relation is difficult to observe directly, but it is important for interpreting swarms. Some migrating sequences may be the seismic edge of a broader zone of quiet slip. Others may be driven mainly by pressure or stress transfer among small faults. The depth distribution helps separate these possibilities. In Nevada, crustal earthquake depths are part of a larger pattern of distributed deformation. The state does not rest above a single simple subduction zone or a single transform fault. It lies within a wide region where extension and shear spread through the continental crust. The brittle layer absorbs this motion through many faults, many small earthquakes, and occasional larger ruptures. Migration becomes one expression of the crust adjusting internally to forces imposed over a broad region. This inner layer is hidden, but not silent. Every recorded earthquake marks a brief failure within rock under pressure. The depths, times, and locations of those failures create a map of the active brittle crust. Beneath Nevada's valleys and ranges, the rock is strong enough to hold stress and fragile enough to break. Migrating earthquakes move through that strength and fragility, tracing the places where the crust approaches its limit and gives way in small, measured steps. Deeper beneath Nevada's brittle crust, the lithosphere carries the broad forces that shape the state over long spans of time. The lithosphere is the rigid outer shell of the Earth, including the crust and the uppermost mantle. It behaves as a strong layer compared with the warmer, weaker material below it. Nevada's earthquakes begin mostly in the brittle crust, but the forces that load those faults extend through the wider lithosphere and connect the region to plate motion across western North America. At this depth scale, the state is not a collection of separate valleys and ranges. It is part of a wide deforming zone between the stable interior of the continent and the active Pacific margin. The Pacific plate moves northwest relative to the North American plate. Much of that motion is taken up near the California coast, but a portion spreads inland. Nevada lies within this distributed zone, where the crust and upper mantle respond through extension, shear, uplift, faulting, and slow deformation. The Basin and Range province reflects long-term stretching of the lithosphere. When the outer shell extends, the crust thins and breaks into fault-bounded blocks. The upper mantle beneath may rise slightly as overlying material becomes thinner. This upward movement can bring warmer conditions closer to the surface. Nevada's high heat flow in many areas is consistent with this extended setting. heat does not act alone as the cause of earthquakes, but it influences the strength and thickness of the brittle layer above. The deeper mantle beneath Nevada does not rupture in ordinary crustal earthquakes. It moves more slowly, over longer times, under high temperature and pressure. Rock there can deform without breaking in the sharp way that produces seismic waves from shallow faults. This slow movement supports and modifies the surface region. It helps determine where the crust is warm, where it is strong, and how strain is shared across the province. Lithospheric thinning is not uniform. Some areas beneath Nevada may be thinner, warmer, or more altered than others. Geophysical studies use seismic waves, gravity measurements, heat flow, and electrical properties to infer these differences. Seismic waves travel at different speeds through cold, strong rock than through warm or partially altered rock. Gravity measurements reveal density variations. Heat flow measurements show how much thermal energy rises toward the surface. Together, these observations indicate that the deep structure beneath Nevada varies from place to place. These variations help explain why seismic activity is uneven. A warmer region may have a shallower brittle layer and more geothermal systems. A cooler or stronger region may store strain differently. A zone of older weakness in the lithosphere may guide later deformation. The present earthquake pattern is therefore shaped by both current forces and inherited structure. Inherited structure means older faults, boundaries, and rock fabrics formed during earlier geologic episodes and later reused under new stresses. The western edge of Nevada is strongly affected by shear related to Pacific and North American plate motion. This shear reaches inward through the Walker Lane. At depth, the lithosphere must accommodate sideways movement without a single narrow plate boundary. The result is a wide zone of distributed deformation. Some of the motion appears at the surface as strike-slip faults. Some appears as rotation of crustal blocks. Some contributes to normal faulting and basin formation. The deeper system supplies the broad stress field in which these surface faults operate. Farther east, extension dominates more clearly. The crust is pulled apart across many basins and ranges. Faults slip in response to this stretching, but the deeper reason lies in the regional force balance of the western United States, the high elevation of the interior, gravitational spreading of thickened crust from older mountain building, plate boundary forces, and mantle processes all contribute to the broader deformation. Scientific understanding supports a combination of influences rather than one simple cause. The elevation of Nevada is also part of the deeper story. Much of the state stands high above sea level despite its many basins. This elevation reflects crustal thickness, mantle support, thermal structure, and the history of western North America. Warm mantle can provide buoyant support, helping keep regions elevated. Thinned crust can produce basins, but the whole province remains part of a high interior landscape. The relation between elevation and deeper structure is complex, and some details remain uncertain. Earthquake migration at the crustal level does not require mantle movement on human timescales. A swarm moving over days or months occurs within the brittle crust, yet the reason the crust contains stressed faults, high heat flow, and fractured pathways is tied to deeper lithospheric conditions. The mantle and lower lithosphere set the long-term background. The upper crust supplies the short-term ruptures. Scientists examine this deep background with care because direct observation is impossible. No instrument can simply view the mantle beneath Nevada. Instead, researchers infer conditions from waves generated by earthquakes, from heat measured in boreholes, from the shape of the land, from gravity variations, and from the chemistry of volcanic rocks. Each method has limits. Seismic imaging may show broad zones but not small fractures. Heat measurements may be sparse. Gravity signals can have several possible explanations. The accepted picture grows stronger when independent observations agree. Volcanic history adds information about deeper processes. Parts of Nevada and nearby regions contain volcanic rocks that record past melting and mantle interaction. These rocks show that heat and magma have influenced the region at different times. Most Nevada earthquakes are not volcanic earthquakes in the sense of magma actively forcing its way to the surface. Still, volcanic history helps describe the thermal and mechanical state of the lithosphere. The deeper system also changes slowly. Plate motions continue year after year. Heat moves upward, the crust stretches by small amounts. Faults load over centuries and longer. Mantle processes evolve over millions of years. Human observation captures only a brief interval. This is why scientists combine modern instruments with geologic evidence. The present pattern of earthquakes is a short expression of a much longer deformation history. At the lithospheric scale, Nevada's migrating earthquakes become small surface signs of a large and patient system. Their paths are controlled by faults and fluids in the brittle crust, but their existence depends on the deeper forces that keep the crust under strain. The upper mantle does not announce itself at the desert surface. It works through heat, support, weakness, and slow motion. Above it, the crust holds, bends, and breaks. In that layered connection, Nevada's active faults belong not only to valleys and ranges, but to the deeper outer shell of the Earth. Hazard models form an inner layer of interpretation, where observations of Nevada's faults, earthquakes, ground motion, and human exposure are brought together into measured estimates of future shaking. A hazard model does not predict the exact time of an earthquake. It does not name the next fault to rupture with certainty. It describes the level of shaking that may occur over a chosen period, given what is known about faults, past earthquakes, crustal motion, and the behavior of seismic waves. The starting point is the recognition that earthquake timing remains uncertain. Nevada's faults move slowly, and large earthquakes may be separated by long intervals. Written records are short, instrument records are shorter, geological records reach farther back, but they are incomplete. Scientists therefore use probability. Probability does not remove uncertainty. It gives a structured way to express it. A model may estimate the chance that a site will experience a certain level of shaking within a defined time span. Fault maps are one foundation of these models. Geologists identify active and potentially active faults from surface scarps, displaced sediments, trench studies, remote sensing, and earthquake locations. They estimate fault length, slip rate, rupture history, and style of movement. Slip rate means the average speed at which one side of a fault moves relative to the other over geologic time. A faster slip rate generally indicates more strain accumulation, though earthquake behavior still depends on many other conditions. Some Nevada faults are well mapped, others are hidden beneath basin sediment or poorly exposed in remote terrain. Hazard models must account for both known faults and background seismicity, which means earthquakes that may occur away from mapped structures. This is important in a region where active faults may be buried, segmented, or difficult to recognize at the surface. A model that includes only visible faults would miss part of the hazard. Earthquake catalogues provide another foundation. They show where earthquakes have occurred, how large they were, and how activity changes through time. Small earthquakes help outline active zones, including migrating swarms. Larger historical earthquakes show the capacity of faults to produce damaging shaking. The catalogue must be handled carefully because detection has improved over time. Modern instruments record many small events that older networks missed. Scientists correct for these changes when estimating long-term rates. Ground motion models connect earthquake sources to expected shaking at a site. They estimate how seismic waves weaken with distance and how they are affected by magnitude, depth, fault type, and regional rock properties. These models are built from recordings of many earthquakes. Nevada has its own regional conditions, but large damaging earthquakes are infrequent. So scientists also use data from similar tectonic regions. Each model contains uncertainty, and hazard studies often compare several models rather than relying on one. Local ground conditions are central for cities: bedrock, shallow soil, deep basin sediment, groundwater, and topography can change the shaking that reaches buildings. A valley filled with soft sediment may amplify some waves. A ridge may experience different motion from a nearby flat plain. The Las Vegas Valley, the Truckee Meadows, Carson City, and many smaller basins each have their own subsurface conditions. Hazard models become more useful when they include these local effects, though detailed mapping is not complete everywhere. The result of a hazard model is often shown as expected shaking intensity or acceleration, but the scientific meaning is broader than any single number. The model combines many possible earthquakes on many possible faults, each weighted by estimated likelihood. A site's hazard may come from a nearby moderate fault, a more distant larger fault, background seismicity, or several sources together. The final estimate is a layered calculation of many uncertain possibilities. For infrastructure, hazard estimates guide design. Bridges, hospitals, schools, dams, power lines, pipelines, and communication systems need standards that reflect expected shaking. A highway bridge across a basin may require different design attention from a small building on bedrock. Critical facilities often use more conservative standards because their failure would affect emergency response and public safety. A model helps engineers choose design levels, but engineering judgment and site investigation remain necessary. Urban planning also uses hazard information. A mapped fault trace may influence where certain structures should or should not be built. Soil studies may identify areas prone to liquefaction or settlement. Landslide and rockfall hazards may matter along steep range fronts. In Nevada, where development often follows valley floors and mountain edges, these local studies connect broad hazard models to practical decisions on the ground. Migrating earthquakes contribute to hazard understanding without becoming simple alarms. A swarm may reveal a hidden fault, improve knowledge of stress changes, or show that a geothermal or tectonic area is active. Most swarms do not lead to large damaging earthquakes, so their presence alone cannot be treated as a prediction. However, they refine maps of active structures and help scientists understand how the crust responds to pressure and stress. Over time, this information improves the background used in models. Uncertainty is not a weakness of hazard modeling. It is one of its central subjects. Scientists describe uncertainty in fault slip rates, rupture lengths, recurrence intervals, ground motion behavior, and basin effects. They also distinguish between what is known from observation and what is inferred from models. This careful structure helps prevent false certainty. It allows planners to act under incomplete knowledge, which is necessary because waiting for perfect knowledge would leave communities exposed. Hazard is not the same as risk. Hazard refers to the expected shaking or ground failure from natural processes. Risk includes the people, buildings, lifelines, and economic systems exposed to that hazard. A remote basin may have high earthquake hazard, but low human risk if few structures are present. A city may have moderate hazard but high risk, because many people and systems are concentrated there. Nevada contains both kinds of places. Modern hazard models are updated as new data arrive. A newly mapped fault can change local estimates. A large earthquake can reveal unexpected rupture behavior. Improved satellite measurements can refine deformation rates. Better seismic networks can identify active zones beneath basins. Engineering records from earthquakes in other regions can improve ground motion models. The work is continuous because the understanding of the crust continues to sharpen. For Nevada, the goal is not to declare that millions will certainly be harmed. The goal is to recognize that millions live, travel, work, or depend on systems within a region of active faults. The threat lies in the combination of seismic hazard and exposure. Models help make that combination visible before strong shaking occurs. They turn scattered evidence into a practical map of possibility. Beneath the calm surface of valleys and cities, uncertainty remains, but it is observed, measured, revised, and used to prepare the ground more wisely. Prepared ground begins with accepting that Nevada's earthquake hazard is real, uneven, and partly uncertain. The state contains active faults, migrating swarms, geothermal systems, growing cities, and long corridors of infrastructure. It also contains wide regions where few people live. This mix means that hazard and risk do not appear in the same way everywhere. The science describes where shaking is possible and how strong it may be. Preparedness describes how communities reduce harm before the ground moves. The first part of preparedness is knowledge of place. A building on shallow bedrock faces different conditions from a building above deep basin sediment. A road crossing a fault scarp faces different concerns from a road crossing a stable plain. A pipeline near a river may need attention to liquefaction, while a mountain road may need attention to rockfall. Nevada's landscape requires local understanding, because the same earthquake can affect nearby sites differently. Mapping is one practical form of that knowledge. Geologic maps show faults, sediments, slopes, and young deposits. Seismic hazard maps estimate likely shaking levels. Soil maps and engineering studies describe how the ground may respond. These maps are not final truths. They are tools built from available evidence. They improve as scientists collect new data from fieldwork, instruments, trenches, satellite measurements, and earthquake sequences. A migrating swarm may refine one small part of a map by revealing an active structure that was poorly known before. Building design is another part of prepared ground. Modern seismic codes require structures to resist shaking in ways that protect life. They guide foundations, connections, walls, frames, and materials. Good design does not mean a building will remain undamaged after a strong earthquake. It means the structure is intended to perform in a controlled way, reducing collapse and allowing people to survive. Critical buildings require special attention because they support response and recovery. Older buildings are a particular concern. Some were constructed before modern seismic requirements. Some use unreinforced masonry, weak connections, or irregular shapes that perform poorly during shaking. Retrofitting can strengthen these structures. It may add bracing, reinforce walls, improve roof connections, or strengthen foundations. The work is often gradual because it requires money, planning, ownership decisions, and public policy. Yet each strengthened structure reduces future loss. Infrastructure connects the risk across distance. Water lines, power systems, fuel routes, communication cables, bridges, and highways allow modern Nevada to function. Their failure can spread the effects of an earthquake beyond the area of stronger shaking. A broken water main can affect firefighting. A damaged bridge can slow emergency movement. A disrupted power line can affect hospitals, homes, and businesses. Preparedness therefore includes lifeline planning, redundancy, inspection, and repair capacity. Emergency planning depends on realistic scenarios. Scientists and planners create earthquake scenarios to examine what could happen if a known fault ruptures near a city or corridor. These scenarios are not predictions. They are structured exercises that combine fault information, expected shaking, building inventories, population data, and infrastructure maps. They help reveal weak points before an event. They also help agencies plan communication, shelter, medical response, debris removal, and restoration of services. Public awareness matters, but it must remain steady rather than fearful. Nevada's frequent small earthquakes do not mean that disaster is near. They do mean that the ground is active. A calm message helps people understand the difference between ordinary seismicity, a notable swarm, and a damaging earthquake. Preparedness works best when it becomes a normal part of life, like maintaining roads, checking water systems, or updating building standards. Scientific uncertainty must be communicated plainly. Observations indicate that migrating earthquakes can result from stress transfer, fluid pressure changes, slow slip, or a combination of processes. It remains uncertain which process controls every swarm. Most swarms end without a damaging earthquake. Some may reveal faults that deserve closer study. This balanced understanding avoids two mistakes. It avoids ignoring swarms as meaningless, and it avoids treating them as certain warnings. Monitoring supports preparedness by shortening the time between observation and understanding. Dense seismic networks can detect changes in earthquake patterns. Strong motion instruments record shaking that engineers use after events. Satellite radar can map ground deformation. Global Positioning System stations measure slow crustal motion. Together, these tools create a living view of Nevada's active ground. They do not provide exact prediction, but they improve situational awareness and long-term planning. After an earthquake, rapid information becomes essential. Scientists estimate location, magnitude, depth, and expected shaking. Engineers inspect bridges, dams, hospitals, and public buildings. Utility crews search for breaks. Emergency managers compare reports from the field with maps of likely damage. The quality of preparation before the event determines how quickly these actions can begin. A prepared system does not eliminate disruption, but it reduces confusion. Land use decisions also shape future risk. Growth near fault zones, on soft sediments, or along steep range fronts can increase exposure if hazards are not considered. Development can still occur in many areas with proper study and design. The important point is that geologic information enters decisions early, before roads are placed, schools are built, or utilities are buried. Preparedness becomes less costly when it is included from the beginning. The phrase threatening millions should be understood with care. Millions of people live in Nevada, visit its cities, travel its highways, or rely on infrastructure crossing active regions. This exposure makes earthquakes important. It does not mean that millions are expected to be harmed by a single migrating swarm. The threat is broader and quieter. It lies in the long-term meeting of active faults and expanding human systems. Prepared ground also includes respect for limits. Scientists can identify active faults, estimate likely shaking, and explain possible swarm processes. They cannot state the exact day, size, and location of the next damaging earthquake. Engineers can design safer structures, but no design removes all risk. Communities can plan response, but every event brings unexpected details. Preparedness remains an ongoing practice rather than a completed task. Nevada's earthquake story therefore settles into a practical understanding. The desert surface is not motionless. The crust stretches and shears. Faults hold stress and sometimes release it. Small earthquakes migrate through hidden pathways. Cities and lifelines occupy basins and range fronts shaped by the same forces. Science listens, maps, models, and revises. Preparedness turns that knowledge into quieter strength, so that when the ground moves, the places above it are less fragile and more able to recover. The ground grows quiet again in the last light of the desert. Across Nevada, the ranges hold their long shapes, and the basins rest under open air. The surface appears still, yet the deeper earth continues its slow work. Faults remain within the crust. Heat remains below the rocks. Water moves through hidden spaces. Stress gathers and releases in small steps, sometimes in clusters that travel through the dark. Science follows these movements with patient instruments and careful maps. It does not turn uncertainty into certainty. It makes uncertainty smaller where evidence allows. It shows where faults lie, where basins may shake strongly, where fluids may influence swarms, and where people and lifelines meet active ground. Each measurement adds to a quieter form of safety. Nevada's migrating earthquakes are not signs of chaos. They are traces of a layered earth adjusting through time. Some are shaped by stress, some are shaped by fluids, some remain partly unexplained, most fade without great damage, but each one helps reveal the structure beneath the valleys. Above them, cities, roads, and power lines continue under wide skies. Preparedness does not remove motion from the earth. It gives the built world a steadier way to live with that motion. In the calm after study, the land remains what it has long been, a dry and open place where deep forces move slowly beneath the quiet stone.